There's been a lot of excitement in time series with the addition of the Kolmogorov-Arnold network time series models. What I want to do today is we'll start with going through a toy example of the model where we'll use that to look at this particular data set. We'll bring up this model, define it, even modify the architecture a little bit, run that through, take a look and see how well it does, training losses, the predictions, taking that apart to give us a conceptual understanding. After that, I'm going to take an implementation of this network by Nixtla, and we're going to benchmark that on the M3 and M4 datasets, showing you how to do all of that as well. So let's start with this Google Colab notebook that has the network, and you can run this on CPU. This is, again, the toy dataset that we have. As we go through this, you'll see that we've created first just a generic time series data set, so we have something that we understand what it looks like to see how well the model is doing. So I'm going to go ahead and create that data set. One decision here that's important is the number of steps that I want to make for predictions. Do I want to predict one time step ahead, multiple time steps ahead? That's a decision, and as you play with this, you can actually vary that a little bit as well. So we're going to create that. The rest of the code here is going to go ahead and create our test train split that we'll use for this as well. Now, whenever you're doing this stuff, and this will come up several times here, is have a baseline, have some other one to approach it to. So here we're going to use a simple multi-layer perceptron neural network. That's going to be our baseline model to run our comparisons again. Now, this is the initial implementation of the KAN model that we're doing. Again, the KAN model takes complex functions, breaks them up into univariate functions. So you can see here the different univariate functions we have. I've got them highlighted here. Then takes those univariate functions, sums them all together to represent the complex function. And here we'll see here is the function that combines all those pieces. We'll do some variations of this to give you the hang of it, but that's the basics of how that works. And then, of course, we run that forward pass through that across all those different step sizes that we had. After that, we have our train model here, typical kind of Pytorch setup for running that through, training the model there as well. We're going to evaluate on a test set. Now, when I run this through, the first piece is, let's run this on the MLP model. You can take a look. I set it at 10 epochs. I've played around with this a little bit. I know where to set it at. We can see exactly how well the model's doing. MLP model does pretty good. Now, I take that same KAN model that I've created earlier. I'm going to run that through. Here, I've set it to 20 epochs because I know it takes a little bit longer to run. The KAN model is also just a little bit slower as well. And of course, that can depend on the setup of how complex that KAN function is to do that. So we can see right away, its first pass through, this KAN model in this case here is actually coming up with a decent test loss. We can visualize the training and test losses. This is always important to do because you want to make sure that your model is continuing to learn and is not overfitting the data. We always look and see what is our test loss here. We want that test loss to continue going downwards. If we ran this too long, you'd see it overfit, and our training loss would go down to 0 because it would perfectly learn the training data, but it wouldn't be able to generalize because of that high test loss. We always want to do visualizations as we go through this. So I've got a little bit of code here for visualizing the predictions of the model, and we can see how well the models do. Beyond that, we have higher metrics we can calculate. So this first pass you'll see is the KAN is doing slightly better than the MLP model here in terms of mean average error, which we want a smaller mean average error like that. Let's start playing around with it and trying to understand what's going on. So one thing we can do is we can plot the different functions that are inside that KAN model. So I have a function here that goes through step by step of each of the features that we have. What does the output look like for each of those features? Because we can kind of try to take this model apart a little bit And once we do that, we can see here, for example, and I have it running for 4 time steps. We can see for feature 1, and a lot of these should be on a line. As you can see, for feature 1, for example, if the input value is 0, it's going to output 1. If its input's 1 on average, right, it's around 2. But we can see kind of shape of that univariate function that we have. We can do the similar things for other features as well. In this case, I've built this model for a 4 time step piece. But so now what I wanted to do is show you another model, because part of the joy and the variety of these Kolmogorov-Arnold models is you can change those univariate representations, how it's doing that, as well as how it's combining the piece. That's where I think the excitement is. And let me again preface, I'm not a super expert. I haven't spent a ton of time on these models, but these are the intuitions that I've picked up from reading the literature. And again, like, I'm only going a little bit deep. Lots of papers on this, lots of other great research. So treat this as an introduction to the topic, not the definitive piece. So here I just played around with the idea of, hey, we can have different univariate functions. So why not? I'm going to create maybe a linear layer here. I'm going to do a sigmoid over here, right? We have another linear with a Leakey-Rayleigh as an activation function. So just, we're going to treat the information that comes in differently for different univariate, differently for different functions. This is one of the joys of these types of models we can do. So I run that through. We have a different kind of forward pass like that. And you'll see the model even has a little bit, I think, lower of a test loss than earlier. This complex model takes a bit longer to run, but does a little bit better. And you can see here kind of the nice training loss curves match up nicely like that. And so then when I run the evaluation, you can take a look at the predictions, kind of play around with that as well. But now when I plot those same kind of univariate functions, this is where I can have a little bit more fun. So for one thing is, you can see here when we kind of sum all the pieces together, that again, they kind of look like straight lines and stuff, but you can see kind of the curves of the sigmoid function. You can see kind of the activations here like that. So this is where kind of having those different types of univariate ones will show up. And here, what I'm doing is, in this last function here, is we're going to go through all the different types of passing each output of the model separately, because when we look at how we've constructed this particular complex model, we'll see here we've built in kind of this 8 layer here, not 8 layers, but has 8 different outputs like that. And when we go and we look at it, we can actually even trace out and see how the model responds for each of those. And so you can see here each of the outputs. So this is how you can start looking deeper inside the architecture as you start playing with it, as you start trying different architectures like that. Again, this is a 101 tour. Play around with it. Take a look at other papers to go deeper. So that's the beginning to play with it. Now, luckily for us, the folks over at Nixtla have already taken KAN and implemented it inside their neural forecast library. And it comes with a ton of options. We're not even going to use all the different kind of options that are available here kind of in the model. You can see like that. They've run some experiments on this. Some of the stuff that I'm using is from them in terms of their running their benchmarks on Auto 3 and 4. They're even doing some cool things like building an AutoCAN model that you can automatically hypertune it. So check out that library for kind of more details, but let's start playing around with this a little bit on ourselves. So I'm going to go ahead and fire this one up. Now for this library, we're going to use a really large data set. So I'd recommend when you use Google Colab here is you want to have a GPU, because otherwise it's going to be dirt slow for running this. So let's get this connected. I'll get this running along the way like that. I'm going to just hit runtime run all, or let's just step through this. We're going to install the all the different Nixtla packages we need like that, get the dependencies going as well. Once the packages are installed, let's go ahead and install the M3 dataset. So Nixtla has a package to make this easier to do. The M3 and M4 are very popular real-world datasets that people often use to benchmark these. The M3 dataset here we're using, you can take a look at the head. You'll see that it's a monthly dataset. It's also univariate. There's only the Y that we're going to do. Often for real-world time series, you're going to want to add more features, add more exogenous features, variables, whatever you want to call them, because those often give you more signal like that. Don't always have that, but if you can, include that. So here's a sense of that data that we can take a look at. For running this notebook, I want to do this interactively. I'm going to bring this down to 10 series. In my experience, 10 series runs very quickly. Once you get to 100,000, it runs a bit slower. It's not the fault of the CAN models, as we'll talk about like that. So now that I've picked 10 unique series that we're going to run, let's next take a look at the models that I've chosen to work with. Oh, I need to talk about Horizon. What we're going to do here is predict for the next 6 months. So I'm going to have my input data that comes in, and then I'm going to predict the next 6 months out is the goal to do that. Now, in terms of the input data that's going to come in, we'll see here that the input size for the neural models is set at twice the horizons. So that means input size is going to be 1 year, 2 times 6, 12 months of data that comes in. And that's going to be a sliding window as we move into the future. This is often the way we set up neural forecasting models and machine learning models, where there's a fixed size that comes in. We don't want to train on all that different training data that goes days, years, months back. Having that fixed size also makes sure that our model architecture is easy to kind of run through everything as well. We don't have to account for varying lengths like that. Using early stopping here, we don't want to train any longer than we have to. So I've set as my baselines the KAN model. I'm just using the default options largely that come inside of Nixtla. We're also running, again, a simple neural network MLP model. And then we have NBeats, which is another popular neural forecasting model that does very well. I often like to compare these things to baseline statistical models. So here I've picked ARIMA, a very simple ARIMA where I've set the kind of the order at 1, 1, 1 like that. I've used Nixtla's AutoTS, so this is an exponential smoothing, another statistical function. And the last two here are really just very simple baselines of naive functions where we're just going to basically predict what based on the last number that we've received like that. It's a very crude, very easy, but as you'll see, it gives you a strong baseline for lots of different pieces like that. At this point, I should always remind you, like, these notebooks, yes, you can run these end-to-end, but they're really built for exploring. So all the different pieces I'm taking here, you should be adding cells, checking things, look at the inputs, outputs of this if you want to truly kind of learn all this stuff. Otherwise, just running the notebook straight end, you're not going to pull everything out. So now let's go ahead and we'll pull this up. The first thing I'm going to do is run the neural forecasting models. You can see how easy it is to do in Nixtla. Literally, like, I have 3 models. They're right here inside neural models. I've set the frequency here for monthly, and then I run the fit, run the predict. It's so easy to kind of be able to run and do that. So I'm going to give this 1 minute here. It runs very quickly across all these different models. The next thing I want to do is run the statistical models. I'll warn you, the statistical models do take a little bit longer to run. You can see in this case, with just a handful of series, they run very quickly as well. So the next piece I have here is running some of the statistical functions, pulling all that together. I'm going to run in a separate, I don't want to mess this code up simply because there's something I want to show you. So let's go ahead and I want to take a look at those statistical predictions and show you what they look like here. So let's take a look. And one thing you'll see here is look at these naive ones and the seasonal naive ones here. What they're doing, again, these are very simple baseline models. They're taking that last value that was given And the naive is just predicting that for the next 6 months. Seasonal naive takes the season into account and has that built in. But understand just how simple these models are compared to the other models that we're using. Now, when we go and we compare these models, I had run this earlier on lots more data, so I want to go over the results with lots more data than that sample of 10 that I've shown you. And here, when we take a kind of a look at these, there's 3 different metrics I have here. We have the MAE, the mean average error that we're going to use about. And mean average error, we'll see that just running this as a simple naive model, the mean average error is 677. That's a great baseline that you want to start comparing it, because now when we see that 677, we see that, oh, using a simple ARIMA model is a little bit better than the baseline, but what is it? 10% better than that naive like that. So this is where you got to keep in mind exactly how much better these are, because when we get over to looking at the NBeats or the KAN models, you'll see that the numbers here are starting to get very close in terms of that differentiation, especially compared to the size of what we're doing. Now, I always like to compare against those naive baselines using the MASE metric. I like this because I can kind of compare and see what's the percentage difference between them because they're scaled to 1 like that, where I can see that, for example, that there's about a 2% difference between how much better NBeats is doing than MLP. So this is where like MASE is often my go-to in terms of when I'm talking about all these metrics with this. Now, the example I've done here with the evaluation, I've only used 1 validation data set. I forgot to show you it earlier. The test set here is just the last 6 months. I could have used a much larger test set. I could have used a test set of varying areas, of varying time pieces too. So the test set here is rudimentary. I don't want you to think that that's always how you kind of measure these things as well. Always good to use multiple metrics to get a good sense of this. Now, often when you're working on things where you have multi-series, where here you have 1,400 possible series, you're always going to look at the errors and see like, hey, are there similar clusters that are having similar types of errors? Because clustering in multi-series is often a great way to get a little boost, because one approach won't fit everything. But if you can cluster these with different approaches or use different data, you can often get an overall much better performance. It's hard for me. I can't see all of you out there, so feel free to kind of add questions if I've covered something too quickly. Off the top of my head, these are the things that I think pop out that are important to kind of know as you go through this. So I've went ahead and taken all these, created a quick little graphic to kind of see the difference here, where this was run on about 1,000 of the 1,400 series. You can see the KAN model in this case really didn't do much better. The NBeats model did better, but the statistical approaches over here of the auto ETS here was the best particular model for this. So this is where in time series, a lot of the times these simpler approaches often seem to do better. All right, if we keep going in the notebook, I didn't want to have 1 data point. I wanted a little bit another data point. So I ran using the M4, which is another well-known kind of time series. I ran this on a daily forecast. And I've set this to use the last 7 days. So this is exactly where I set the test set, the last 7 days. You can change this. Try different lengths of test set. This is an important thing to consider. Whenever you're evaluating your models, you want that test set to reflect not just the last 7 days, but you want it to reflect what your data looks like, especially if you have seasonal trends, things that change. If Christmas is the time that you care about, well, maybe your test set should be Christmas and not necessarily the last 7 days of your data set. These are things to think about kind of as you're setting it up here. So I've set this for daily with the last 7 days for the test set to run this. Now in this case, I didn't break up the data in across lots of different cells. I just have it as one big chunk. It was just easier for me to kind of run it this way as well. So however you want to, kind of makes a difference for you, but that's why just the code looks a little bit different like that. So try these notebooks out, whether it's the toy data set and you're just trying different architectures out, or you want to move to production. Nixtla is a great way to start. I think they're just beginning with all of this. I should also point out that KAN is just one of many algorithms. Look at all these algorithms over here that Nixtla has that are neural network algorithms. So there's a ton of stuff if you're really into this and want to try out and experiment more. As you do this, let me know what you find out. Time series is always fascinating to me. Thank you all.